Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study. It's my pleasure to welcome you here most warmly to this celebration of the 80th anniversary of the founding of the Institute, and in particular to this lecture by Frank Wilczek. Frank is, of course, no stranger to Princeton nor to the Institute. He took his PhD in physics at Princeton University in 1974, having taken his bachelor's degree in mathematics at Chicago. After holding professorships at Princeton University and at the University of California, Santa Barbara, Frank was a member of the faculty of our School of Natural Sciences from 1989 to 2000. He is now Hermann Feshbach Professor of Physics at the Massachusetts Institute of Technology. Frank's contributions to a broad range of areas of physics have been very widely recognized by the most prestigious awards, including the Nobel Prize in Physics, which he shared in 2004 with David Gross and David Politzer, awarded for their discovery of asymptotic freedom, which provides the basis of our fundamental understanding of the forces which hold the atomic nucleus together. Frank is also a very successful writer of books aimed at explaining physics to a general audience. At the end of this lecture, there'll be an opportunity for questions, and that will be followed by a reception in the Ford Hall Common Room, to which you're all invited. Frank's title today is Quanta, Symmetry, and Topology.
Thank you. Well, it's really nice to be back at Princeton. I was very happy to walk around the pond and see that you've still got frogs and turtles now. The Institute and Princeton are very famous for cultivating the deep relationship between mathematics and physics in our understanding of the world. And so I thought it would be appropriate on this occasion to talk about some of those deep connections as they're at the frontiers of the subjects today and as they might develop into the future. So I will first discuss the problem of decoding nature's quanta, nature's building blocks. And as you'll see, this is a study in symmetry. This is a dodecahedron, one of the perfect solids or platonic solids of the Greeks. It has 12 sides, each of which is a regular pentagon. There are very few perfect solids of this kind. There are only 5 that the Greeks already knew about. That is, solids made out of regular polygons with all equal sides, and all polygons the same. The dodecahedron is particularly nice because it's an example of a very symmetrical object. That is, there are many transformations you can make on it. For instance, rotating around an axis through the top and the bottom by 1/5 of 2 pi. We'll take this whole object into itself, but changing the relative parts. And of course, an arbitrary lopsided object that didn't have so much symmetry would not look the same if you made such a rotation. So dodecahedron is a special object that has lots of symmetry. There are lots of things you can do to it that could have changed it, but in fact don't. It's also nice because you can make calendars out of it. And that's a handy thing because it has 12 sides and rests nicely on its bottom. Now, the dodecahedron is so famous and so special that if you were handed something like this and weren't told what it was, you could infer what it was. This is clearly meant to be a dodecahedron, and you're meant to fold it up, and that's what it is. But suppose somebody handed you this. Suppose some evil spirit erased part of it. Well, if you had studied mathematics and symmetry, you'd realize that there was something very special about pentagons, regular pentagons, and that this could fold up, and if we could supply the missing pieces, this is really still meant to be a dodecahedron. Okay, keep that in mind. And now let's look at our knowledge of the basic building blocks of nature as summarized in the so-called standard model of particle physics. It would be difficult to overstate the success, the precision, the mathematical beauty, and the proven accuracy of the standard model. One aspect of its beauty is that without doing it much injustice, you can summarize its content just by writing down what the building blocks are and how they transform under three different kinds of transformations, different kinds of symmetry, that in this case don't move things in space but change one kind of particle into another. So we have transformations that leave the content of the theory unchanged, but change, say, red quarks into blue quarks and vice versa. And these kinds of transformations are called the color SU3 symmetry, because there are three colors, and every quark comes in three colors. Similarly, there are transformations that move you vertically in this direction. And the only other interaction that's in the standard model is an interaction that doesn't change one particle into another, but responds to the different particles. And the strength of the response is encoded in these funny numbers that you see at the side. And this one is 0. And that's it. This is an honest portrayal of our deepest knowledge of most of physics. If you had a course in relativistic quantum field theory and group theory, you would be able to, from this picture with no other information, reconstruct essentially all of chemistry, all of astrophysics, all of material science, and so forth. You'd have to be very gifted at calculation, but you could, in principle, these are the laws that do it. There's nothing suppressed here. And so it's extraordinary. But given that it is so powerful and so complete, it's a little disappointing. This is God's last word, or close to it. And why are there three different forces? And actually, this leaves out gravity. We'll come back to gravity later. There are three forces. We would expect that in a really fully coherent, satisfying theory, there should be one basic force. And there are 6 different kinds of matter, basic building blocks, that are unrelated to each other. Okay, there are transformations involving these interactions that relate all these particles to each other, but none of them in this group get related to this group or this group or this group. So there are 6 independent ones, and also there are these funny numbers that are just taken from experiment to parameterize the strength of the third interaction. So this should remind you of that. 3 different pieces that seem to be unrelated, and by mathematical ideas that are similar in spirit to the classification of the different regular solids, we can classify what are the possible ways of extending the symmetries that govern the standard model into a larger encompassing symmetry. There are only a few possibilities. We can try them out, see if by filling out what we need, by putting back things that might have been erased, they fit together, and whether they in fact explain aspects of the standard model that appear random or bizarre when you just look at the standard model as it is. And needless to say, I wouldn't be telling you about this, taking you down this road, if it didn't lead to a good place. And it turns out that one of the simplest possible ways of uniting those different sub-theories, sub-symmetries that we observe in the standard model into a larger symmetry clicks, in the sense that whereas we used to have 6 different kinds of matter that were unrelated according to the transformations that are in the standard model, now they're all related, and in fact they're all on an equal footing. For mathematicians, this is the so-called spinor representation of SO10, and SU3 cross SU2 cross U1, the symmetry of the standard model fits snugly into SO10. And all those lopsided features of the standard model that you had different parts, different kinds of particles forming different groups that were unrelated and seemed to be lopsided in different sizes and have these funny numbers attached, all of them, all of those features are automatic consequences of taking this symmetry as the fundamental symmetry and erasing little parts of it to get down to the standard model. So by filling in a few extra interactions, we get, among only a few possible consistent ways of doing that, we find one that works very nicely. So I won't be able, of course, to do justice to the full beauty and elaboration of this, but just to say that all different possibilities for distributing the different kinds of generalized charges as plus or minus units are realized, subject only to the constraint that we have an even number of positive ones. If I didn't know the names of these particles, but only knew what's in this picture, nevertheless, I would be able to reconstruct all the observed features that they have, and as I said, most of physics as we know it, including even those funny numbers that tell us about the strength of the third interaction. So it's a fantastic correspondence, fantastically beautiful, fantastically precise correspondence between mathematical ideals and physical reality. But at first sight, it seems too good to be true. If there's really only one basic interaction, there should only be one common power that all those interactions have. They should all have the same strength, but they don't. They have names like strong interaction and weak interaction, and the strong interaction really is stronger than the weak interaction. So they're not, in fact, symmetrical and equivalent. There seems to be a distinction among these interactions as to their basic power. In fact, they go in, for reasons you'll see in a moment, I put the strongest ones at the bottom, so the strong interaction is the strongest. The weak interaction is actually stronger than the electromagnetic interaction, but it's short-ranged, once we get into its range, it's stronger than the electromagnetic interaction. And so fundamentally it's stronger. And then the electromagnetic is the weakest. In any case, they're not equal. So that appears to be catastrophic. If they're all the same, they'd better be equal. However, a major lesson that we learn, closely related to the asymptotic freedom property that Professor Goddard mentioned, in our study of fundamental particles and their interactions, is a lesson actually that humanity has had to learn over and over again. That is, there's much more to reality than is revealed directly to our senses. And in fact, what appears to our senses as empty space is actually full of activity. What's shown here are the fluctuations that are occurring everywhere and every when in the field strength, the energy of gluon fields, the things that are responsible for the strong interactions. So when our eyes don't have the resolution either in space or in time to see this structure, but with the help of very fancy microscopes and our noodles, we can reconstruct the laws that govern there and what our eyes would see if they had that kind of resolution, and this is what you would see. So when you think about space and the properties of particles fundamentally, you have to realize that we're seeing them through a distorting medium, that there's all kinds of activity when you look at very short distances that is distorting our view of the particles as they are. It's as if we're fish in turbulent water that are trying to image small objects. We have to make corrections to get our vision right. And one can calculate that this has an effect, that when you make the corrections to see what the underlying power of the interactions is before it's been affected by all these fluctuations, it's different. The strong interaction, at low energy, relatively low energy, or large distances where we actually measure it. For fundamental physicists, large distances means 10 to the minus 13 centimeters. We want to get smaller than that to find the really basic interactions. If we take our equations and extrapolate to much smaller distances, or equivalently in quantum mechanics, higher energies, we find that the strong interaction gets weaker, so its inverse gets stronger, as shown here. And if you plot it this way, as logarithm of energy versus inverse coupling strength, you get basically a straight line, like that. Okay? So, now we don't have to be satisfied with these couplings being unequal. Maybe that's an illusion. Maybe they are actually unified and equal once we correct our vision and look down to fundamentals at short distances. So let's calculate and see. If we do the same thing now for the strength of the weak interaction, sure enough, there is a short distance where they become equal, so maybe the things do unify. Now, this calculation is not as impressive as it could be because two straight lines do tend to meet in a point. Actually, there are a lot of things that could have gone wrong. They could have diverged. They could have met too soon, in which case the unification would predict a lot of exotic processes from those missing pieces that aren't observed. That would be too strong. But still, so it's a little more impressive than just two lines meeting in a point, but still two lines do tend to meet in a point. So this is not as impressive as it could be. Fortunately, we have a third interaction. So now we can really test. the idea in a stringent way. And here it comes. Don't! Oh. Not quite. Close, but not quite. The experimental and theoretical errors are roughly the width of these lines. So it's clearly not coming together. So what do we do in a situation like this? Well, if we were devotees of the philosopher Karl Popper, who taught us that the goal of science was to create falsifiable theories, we could declare victory, because we created a theory that's not only falsifiable, but actually false. What could be better? But of course, that's not the way we proceed. We don't want to give up on beautiful ideas too easily. They're not so easy to come by at this level. So we look for ways to truthify it. Look for ways of changing things, making them even more beautiful, perhaps. Maybe we haven't been bold enough. Well, we've been pretty bold. We've unified the description of matter so that electrons and quarks, those building blocks, the U and D were the quarks and the E was the electron, fundamental building blocks of matter got unified into one structure. Also, the force-carrying particles, the photon of the U1 and the gluons of the strong interaction SU3 got unified into one structure. That was great, but it still leaves us with two things. So we haven't quite finished the job. Can we do this? That seems like a tall order, and most physicists would have thought it was impossible up until 1970 or so. But then it was discovered by mathematical playing around, really, that it is possible to make a unification of that kind, to have equations that are symmetric between particles like electrons and quarks on the one hand and photons and gluons on the other. It seems very, very unlikely when you first hear about it that you can make transformations on your equations that change all the particles that are like electrons and quarks into particles like photons and gluons, and vice versa, and then still have the same consequences, because electrons and quarks are very different kinds of particles. They are what are called fermions. They obey the Pauli exclusion principle. They don't want to do the same thing. They don't want to occupy the same space, and really that's what's responsible for the hardness of matter, for instance, even though we know that matter consists of atoms that are largely empty space. Whereas photons and also gluons are bosons, so those are particles that love to do the same thing. And when you give photons the chance, they organize themselves into a laser beam and happily are all the same color, all moving in the same direction. That's what they really like to do. So they couldn't be more different, apparently. It seems like you're trying to devise equations that turn apples into oranges and oranges into apples. You want to devise some transformation, some kind of motion that changes one into the other while not changing the content of your laws. And the way that's done in supersymmetry is to introduce an extra dimension, but not a dimension that you can comfortably move around to. It's rather what's called a quantum dimension. And what happens when you move in a quantum dimension is not that you change your position, in the ordinary sense, but rather you change into a different kind of particle. If you were a boson, you change into a fermion. If you were a fermion, you change into a boson. Electric and color and weak charges don't change under this process, but mass changes and spin changes in a very predictable way. And so the symmetry that unites these particles, these apples and oranges, is simply flipping around the top and the bottom of this extra quantum dimension of space. Okay? And as long as you have laws that are symmetric under that operation, you'll have unified the description of those particles. You can't have one without the other. And so, if you allow yourself to move into this extra dimension, it becomes possible to flip the apples into the orange. In fact, it's quite easy. It's really fun. All right. But there's a price. In order to implement this idea, we need to postulate the existence of these new kinds of particles, the particles that the things that particles we know about, like the electron, will change into if they move in the quantum direction. So the electron, for instance, is supposed to move into a new particle called the selectron, which has the same charge as the electron, the same basic interactions, but no spin, and is heavier. Well, when I showed you that picture of space and the fluctuations that it contained, and when I calculated how that affects the unification of couplings, I didn't include these new particles that we have to introduce if we're going to have supersymmetry and complete the unification program. If I want to include those, so if I want to get more ambitious and make the next step of unification, I have to introduce more fluctuations. Those particles also fluctuate and come to be and pass away as virtual particles in what appear to our senses as empty space. So, we want to include them, and if we do that, we get a marvelous surprise. We have to redo the calculation. Now, the slopes of the lines change, and it's just right to make everybody come together very accurately. So that's why I love Susie. But that's not the end of the story. We've left out gravity so far in this discussion. And there's a very good reason to leave out gravity in a simple discussion of unification at first. Gravity appears to be really hopelessly weaker than the other interactions. You see, the difference between the strong interaction and the weak interaction, the difference between their power at the distances where we've observed them, is about a factor of 10. What about gravity? Well, suppose I went up an extra factor of 10. That would bring me a little up there or so. No, that's not good enough. How about another factor of 10? So we're getting up above the top of the building. No, that's not good enough. How about another factor of 10? So we get well into the atmosphere. Nope, not good enough. Another factor of 10. We get into the upper atmosphere. Not good enough. You have to supply 40 factors of 10 until you reach gravity up there. So it's well outside the known universe. And I worked hard to plot it, but you can't, unfortunately, you can't see. However, if you continue the calculation and see how gravity behaves at very High energies, well, according to Newton's laws, which most of us learn in high school, the force of gravity is proportional to the masses of the objects involved. But in Einstein's version of relativity, you have to replace those masses, m, by E divided by c squared. It's really energy that gravity responds to. And so when we're considering very small objects, or equivalently in quantum mechanics, very large energies, gravity gets very, very powerful, very fast. And so if I continue the calculation from gravity being 40 orders of magnitude smaller than the other ones, 40 powers of 10, if I boldly continue from outside the known universe, just keep going, I find that it pretty much unifies as well at the same place. So it's really tantalizing. If supersymmetry's new particles that we had to introduce are going to do this job, if they're going to substantially affect the way the couplings change with distance, they can't be too heavy. If they're too heavy, they don't fluctuate enough spontaneously in space. And so there's going to be a trial by fire. If these particles are actually going to exist and do this job of making the unification work out accurately and quantitatively, some of them have to show up at the great accelerator, the Large Hadron Collider, that's just coming into operation at the CERN lab near Geneva. And if they don't show up in that trial by fire, these ideas will be gone. But another thing that might happen, more optimistically, is we've heard this song, the siren song of symmetry. We're waiting for the verdict of nature to come in. We'll soon see whether nature has been subtle, she's been subtle or malicious in giving us these apparent clues. There we are, there I am, having left behind the safety of the standard model, swimming into these turbulent waters that I showed you about, and there's the siren. We'll see who she is. So, if nothing shows up, that's it. But one thing that more optimistically what might happen is when you examine carefully the complicated collisions that happen at the LHC and analyze them in terms of known particles, you'll find some that don't fit. There'll be some extra things that are not explained by the standard model. And these SUSY particles would say, here I am, somewhere in this mess, and here I am, another one. And then this whole vision will be very much encouraged, and will declare victory. Okay, so that ends the first part of my talk on decoding nature's plan using symmetry. Now I'd like to give the second part of my talk, which will be much briefer, on our attempts to use topology to do justice to new possibilities offered up by our expanded vision of nature. This is a study in topology, another major branch of mathematics. So first, I'd like to convince you that our microverse, very small objects, actually contain gigantic structure. That quantum reality is very big and has enormous engineering potential, still untapped. So let me remind you what classical bits are first. They're arrays of ones and zeros. And by now, in this computer age, it's a very familiar idea that you can encode all kinds of information just as arrays of ones and zeros, almost arbitrary kinds of information. And there are various physical embodiments of this that are used in practical computers. You can embody them as electron spins that can be up or down. So down corresponds to 0, up corresponds to 1. Or more practically, in current computers, thousands of electron spins aligned in a magnetic domain, but still either up or down. And this is the state of your computer. And it could also be on-off states of transistors, with off representing 0 and on 1. Could be lots of things. It could be birds facing one way or the other towards the wall. This is 1, 0, 1, 0. And all kinds of information can be and is stored fundamentally as arrays of many, many classical bits. And computers, those tremendously useful and inspiring devices of modern life, are abstractly, viewed from a sufficiently high perspective, machines for taking one configuration of these spins or bits into another through carefully controlled steps. That's what they do. They take you from one state of information to another in that form. Oops. Okay. Quantum bits are different. Well, if we go to the quantum mechanical description, say of an electron spin, or rather of 4 electron spins, in the classical description, its state was just whether each one of those spins was up or down. In the quantum description, all possibilities are present at once. So the quantum mechanical reality has all these possibilities present. What quantum mechanics tells you is rules for the numbers that multiply the different possibilities. And then when you make a measurement of what the state of the electrons is, these numbers, or more accurately their squares, tell you the probability that you'll reach one result or the other. So for the full quantum mechanical description of 4 spins, you need, as I've displayed here, a 16-dimensional space, 16 numbers. If you think about space, a 2-dimensional space is a space where you need 2 numbers to tell you where you are. 3-dimensional space, 3 numbers. This is a space in which you need 16 dimensions to tell you where they are. And in fact, these are complex numbers, so it's really 32 dimensions. But 16 complex dimensions. With 5 spins, you'd need twice as many. You'd have twice as many possibilities, because on top of each of these, you could have a 0 or 1 at the end. With 6 spins, a 64-dimensional space, it gets very, very big, very, very fast. Okay? Sometimes we argue in particle physics about whether space-time is 4-dimensional or 10-dimensional or maybe 11-dimensional, but that's puny compared to quantum mechanical reality of even a few spins. So this opens possibilities for extremely dense memories. We could have, we pick out a point in this gigantic dimensional space to tell us what the state of our computer is, and also for massively parallel information processing. For instance, in the quantum mechanical version, we can, by swapping the values with the orientations of the first 2 spins or the values of the first 2 bits, we are simultaneously operating on 16 data streams of a classical nature. So we can, and if we have 6 spins, we're operating on 64 data streams simultaneously. It's tremendously parallel processing. If we have 1,000, well, it's an astronomical. We soon go beyond Google's. Sounds great. Lots of room, lots of power to maneuver. There's a catch, however, which is that these quantum bits are very delicate, and unintended interactions with the outside world will make a measurement, determine what particular state of the spins is actually there, roughly speaking, and what's called collapse of the wave function will destroy all this delicate structure. Basically, the problem is the Schrödinger cat problem. Schrödinger, very famously, although he invented quantum mechanics, didn't believe it, and tried to make it look ridiculous by inventing a thought experiment called the Schrödinger cat experiment. So this gives us an opportunity to have a cute cat in the picture. This cat is in a box with a radioactive source. See, there's a Geiger counter, radioactive source. And the radioactive source can have a decay of a nucleus, which is governed by quantum mechanical processes, which will explode a vial of poison gas and kill the cat if the decay occurs. So let's call that the 0. Or if the decay doesn't occur, call that 1, the cat is perfectly erect. So cat dead is 0, cat up is 1. Here's a picture. And what the quantum mechanical reality is telling us is that we have to have both of those things possible, both of those things present in the description of nature, a live cat and a dead cat, a hammer which hasn't broken the vial and a hammer which has broken the vial, a decay which has occurred and a decay which hasn't occurred. Both of them have to be present as part of the description of reality. And then Schrödinger asked, what does the cat think about this? It doesn't seem to correspond to anything in our experience. And insofar as we have empathy with cats, we think that it would be hard. Okay, I guess Schrödinger was too kind to put a human being here, but you could have put a human being and then say, okay, does this hovering between death and life correspond to any conceivable state of consciousness that you've encountered? And the answer is no. And the reason that this does not disturb most quantum physicists is that big objects, like cats or human beings, are constantly being observed, if not by conscious observers, then by gas molecules that are very sensitive around them and very sensitive to their position, and all kinds of things in the external world that are sensitive to whether the cat is erect and alive or down there and dead. And so the wave function collapses and one doesn't have this kind of hovering between death and life, or what's called a coherent superposition of macroscopically different states in practice. So that makes it a challenge to produce this quantum computer, because anything that gets observed regularly, any big object, anything, if we want that to represent a bit that we can manipulate, is going to be very delicate, and like Schrödinger cats, will either will not be able to simultaneously support two different states. Now, I'd like to very briefly and somewhat metaphorically indicate to you how, using ideas from topology, we hope to make tame Schrödinger kittens, so things that will have the quantum mechanical properties, but will not be so delicate, and will also be something we can manipulate. So here's the idea. Topology is the branch of mathematics that's very forgiving to deformations. So if you take a sphere, you can subject it to all kinds of indignities, squash it or stretch it and so forth. As long as you don't tear it, it remains, according to topology, the same object. We'd like to have physical systems that are quantum mechanical systems that have that kind of property. That you can do, the outside world can do its thing, can perturb them, but they retain their integrity. Okay? So what we'd like to have is 0 equals a sphere and 1 equals a torus, which is topologically different. Although the torus can be dented and can have different colors, and it remains a torus even if you poke at it in various ways. And similarly, a sphere remains a sphere. I said this was going to be metaphorical. It's very metaphorical. What's actually a sphere is correlations among many, many electrons in an abstract space, but this gives the spirit of it. So we have these now quantum mechanical objects, which can be macroscopic and therefore robust, and yet represent two different states that we can build up large arrays from. And we have to have a way of manipulating these guys, and that should also be topological, because we don't want the external world to be able to do these kinds of operations. We want them to be very, very special, robust operations that aren't affected by small perturbations. So what we want to do is take these different objects, these different anyons, and have their state be affected only by how they wind around each other. So they get knotted, and as they get knotted, their state changes in controlled ways. So for instance, if you take one guy over another, it might flip the torus into a sphere and the sphere into a torus, flip their bits. And from elementary operations, you can build up very, very complicated things by having basically messy braids or knots that can be. There are many, many distinguishable kinds of operations that you can build up from a few elementary ones. So that's how one can have robust realizations of these zeros and ones that are of a topological nature, and robust operations among them using topologically distinct motions for the different kinds of operations. Where does this lead? Not tomorrow, probably not even next week or next year, but maybe 80 years from now at the next big anniversary of the IAS, or maybe 800 years from now. Well, today, physicists are quite good at predicting the properties of simple materials based on the laws of quantum mechanics and the mathematics of symmetry. A dramatic recent example is the theoretically, ideally simple substance called graphene, which is a single layer of carbon atoms, infinite, in this kind of honeycomb array. Your pencil is what's called graphite. The pencil lead, of course, is not lead, but graphite. It has many, many layers of this, weakly bound together. People had, for many, many years, been after this substance. It was kind of a holy grail of organic chemistry. It's the ultimate organic molecule, all carbon, and infinite in infinite number of rings. But it was only 4 years ago that experimentalist by actually rubbing a pencil at first and on paper, taking Scotch tape to lift off most of the stuff, and then carefully looking for little bits where only one layer was left behind, managed to isolate this substance. Now, after a few years of development, it comes off assembly lines in big sheets. The reason that progress could be so rapid is that we were ready for it. We know how to calculate the properties of these substances, and so we could anticipate their remarkable properties. They have absolutely remarkable properties. They're the strongest material known in the plane, but on the other hand, quite flexible. They're electrically active. They're ideal for touch screens, and they'll soon be on your computers. And you can even get creative because we know how to characterize their behavior very accurately by theoretical calculations. We can, with confidence, design transistors, artificial noses, substrates for organic reactions, and even buildings by putting together graphene. And progress is extremely rapid in this new area. So that's an inspiring story, but it was only possible because graphene is so simple. It's just one thing, and we had the equations in such a form with enough symmetry that they could be solved in a practical way. When it gets to more complicated molecules, like proteins, we don't know how they fold up. We don't know really how they work quantum mechanically by pure calculation. Or, say, high-temperature superconductors, what you get if you put together just a few elements. We can't calculate how those work. So anything really reasonably complex overwhelms the power of classical computers. Basically, because quantum mechanical reality, as we've discussed, is so big, and the classical computer can only handle a very small bit of it at a time. Quantum mechanical computers, however, with these quantum bits, if they're good at anything, they'll be really good at quantum mechanics. So, just as banks of computers have replaced wind tunnels as the method of designing aircraft, in the future, chemistry and material science labs will be replaced by more flexible, more powerful, and ultimately much cheaper labs, which consists of big arrays of anyons. Going even further, eventually the most capable information processing units, also known as minds, will be artificial intelligences based on quantum computation. Those are much more capable in terms of density of memory and in terms of processing power, as we've discussed. Those minds will be delicate. They will only work properly if they're carefully buffered from the outside world. This suggests an answer to a famous question which has bothered Enrico Fermi and bothered me very much, which is, where are they? There's every reason to think that life in the galaxy, life is common. It evolved very rapidly on Earth once conditions were at all allowing. And once things get started, once technology gets started, as in the last 500 years, the activity very rapidly becomes visible from far away. And so, where are they? Well, here's a possible answer. Quite possibly, once they get sophisticated and go to the best kind of information processing, they want to hide in the cold and the dark, because It's very delicate. And so they hide in the cold and dark so they can better explore inner space, which, after all, as we've seen, is much, much bigger than outer space. So, thank you very much for your attention.